Why don't power lines use copper? And what actually makes the wire resist the flow of current? This is one of the most underrated equations in circuits. This is the core idea, resistivity. And you already know Ohm's law. Voltage equals current times resistance. But what determines resistance in the first place? Here's the deeper law. R equals this over this. Let's break this down. Here, this symbol is not P, it's the same symbol that we use for density. And it tells you how much a material resists current. So different materials will have a different resistivity. L is simply the length of the wire, and A is the cross-sectional area. So if you cut it in half and you look at this face, the area of that. What this means in English is a longer wire has more resistance. A thicker wire has less resistance. And resistivity P depends entirely on material. Here's a microscopic analogy which is catchy. And I did use a similar one in the Ohm's law video, but imagine electrons as people running through a hallway. Resistivity will depend on how slippery the floor is. So for example, if it's copper, it's smooth tile, easy to go through. But if it was rubber, then it's a sticky, tangled jungle gym mess. So even if the hallway's length and width are the same, aka the wire size, the floor material, the resistivity, will change everything. Here's an example problem. You're part of a robotics team that's wiring motors, and each motor requires a 30-meter copper wire. They want the resistor to be less than 0.12 ohms per wire. What diameter should the copper wire be? And here's what we're given. The resistivity is 1.68 times 10 to the power of -8, and this is the units that this constant is representative. The length, 30 meters, and the resistivity, well, we want it to be 0.12 ohms or anywhere lower. First thing is we have to solve for this cross-sectional area. And a formula that links everything up is the formula we looked at the start. And this formula and every other formula for this problem is on the free cheat sheet in the description. We can rearrange for A here. Find A equals PL over R. And I'm just going to call this P, it's easier. We can plug in our values. So P being this, length is 30 and 0.12 resistance, giving us an area of 4.2 times 10 to the power of -6 square meters. That's the cross-sectional area our wire should have. Now that we have the area, to find diameter, we can treat this wire as a cylinder. An area of a cylinder is given with pi radius squared. We're looking for the diameter, which we can find if we know the radius. So rearrange for radius with your math skills, and you get radius equals area divided by pi under a square root. Plug in your values for area, which we just solved for, and pi being 3.14. Your radius is roughly 1.16 millimeters, which means the diameter, twice of that, should be at least 2.3 millimeters thick to keep your resistance under control. Here's a follow-up example, and it involves a voltage drop. It's a little more conceptual, but we're going to use the same wire that we just solved a problem about. And that wire, let's say the current that flows through is 5 amps. What is the drop in voltage across the wire? Let's use Ohm's law to find that. If V equals current times resistance, the current is 5, and the resistance is 0.12, which means that it's 0.60 V. So the wire itself loses 0.6 volts. That's why short, thick wires matter, especially in low voltage systems. One more conceptual example. Let's say you have a copper wire and you stretch it out to twice its length while keeping the volume the same. What happens to the resistance? Since the length doubled but the volume stayed the same, that means the cross-sectional area must have been compressed, it halved. So if you look at the resistance, even with our resistivity formula, we doubled the length and we halved the area, which equals a 4 times increase in resistance. This is why wire design matters so much. If you have a thin, long wire, it's very bad for the current. There's a ton of resistance. How about temperature? How does temperature play a role in here? Most metals resist more when it's a high temperature. This is because atoms vibrate more and they interfere with the flow of electrons. So resistance is stronger. The formula for this, also on the cheat sheet, is resistance at a temperature equals this times 1 plus this minus this. And here's what each part means. RT is the resistance at a temperature. R0 is the resistance at a base temperature, for example, 20 degrees Celsius. This symbol here is the temperature coefficient, and it depends on the material. And T is your new temperature. So for copper, a rise from 20 degrees to 70 degrees increases resistance by about 33%. So let's go through an example problem to make some sense of this. The goal is to use resistance to measure temperature. You have a platinum wire with a resistance of 150 ohms at a temperature of 20 degrees Celsius. Inside a mystery fluid, if you store it inside this fluid, the resistance raises up to 170 ohms. What is the temperature of this fluid? Let's use our formula, which you can get on the free cheat sheet in the description, and we're going to rearrange for what we're looking for, which is the temperature after resistance goes up. So this is where math skills come into play. You need to rearrange and isolate T, our new temperature, and it's equal to this equation. If we plug in our values, so our original temperature being 20 degrees Celsius and our change in resistance being that, dividing it by the temperature coefficient of our platinum wire, which is 3.9 times 10 to the power of negative 3, multiplied by the original resistance, 150, we get an answer of roughly 54.2 degrees Celsius. So the fluid is 54 degrees Celsius. This is how resistance thermometers work. They're precise and they work where things like mercury or alcohol and normal thermometers don't work. So a quick recap is that resistance depends on length, thickness, and the material. Resistivity, represented by this symbol, is a property of the material.